Hello and welcome to problem 23 in my Calculus 3 or multivariable calculus problem solving series. In this video, we're going to look at how to use Green's theorem to solve line integrals. So let's go ahead and look at what is Green's theorem and how it can be used to solve or simplify line integrals. So let's say that you have a curve C on the xy plane. And C is a closed curve, meaning that its starting point is the same as its ending point. So it completes an entire path, and C also rotates counterclockwise. So it goes in the counterclockwise direction. And you have a vector field F, which is equal to P comma Q. What Green theorem says is that the line integral of f along C is equal to the double integral of D, which is the enclosed area of the curve, the area which the curve encloses, of the curl of f, or the partial derivative of q with respect to x minus the partial derivative of p with respect to y. And so this here will help us simplify line integrals. And the second part of Green's theorem says that the flux, or f dot n, is equal to the double integral of d of the divergence of f, or the partial derivative of p with respect to x plus the partial derivative of q with respect to y. And so these two theorems, or this one theorem, will help us solve and simplify these line integrals. So what exactly is the curl or the divergence of a vector field? Well, the curl of a vector field is the tendency of that vector field to rotate or curl around a point, while the divergence is kind of like the opposite. It's the tendency of the vector field to diverge away from the point. So let's go ahead and look at an example. Here we have the line integral of along C, a curve, of x times y dx plus x squared times y squared dy. And C is this curve here, which follows this triangle, which has this side of 2x, and this point is 1, 2. And the green area is what we're going to use for our Green's theorem, the double integral. So we need to define our bounds for the double integral that we're going to use for Green's theorem. So to define our bounds, I've written them here. So x is b from 0 to 1. So from here to here. And y will be from the line y equals 0 to y equals 2x. Then we have to find the curl for f, and in this case p is x times y and q is x squared times y cubed. And so remember that the curl is this part here, which is the partial derivative of q with respect to x, or 2x y cubed, so this part here, minus the partial derivative of p with respect to y, or x. So our curl will be 2x times y cubed minus x. And so now we can define our double integral using Green's theorem, and it will be the double integral from 0 to 1 for x, double integral from 0 to 2x of 2xy cubed minus x dy dx. And so now we can solve this like any other double integral. So the first integral gives us 1/2 xy to the 4th minus x times y from 0 to 2x. And then that evaluates into 8x to the 5th minus 2x squared this is dx. And then we finally do the last integral, and we get 4 over 3x to the 6th minus 2 over 3x to the 3rd from 0 to 1. And that's just 4 over 3 minus 2 over 3, or 2 over 3. And that's going to be our final answer. So the circulation of f will be 2 over 3. So let's go ahead and show that Green's theorem works by solving the line integral how we would normally solve it, and just do it. So here we have f, which is equal to x times y, comma x squared times y cubed. And we want to take the line integral along C, this curve, of x times y dx plus x squared y cubed dy. So for this problem, we're going to split it up into 3 line integrals from here to here, from here to here, and from here back to here. So the first one that we're going to look at is from 0, 0 to 1, 0 along the line y equals 0. So when y equals 0, in our integral, it will be the integral of x times 0 dx plus the integral of x squared times 0 dy. So that just is going to equal 0. So the next portion that we're going to look at is from 1, 0 to 1, 2 along the line x equals 1. So this one right here, this vertical line. And x is equal to 1. So when we plug that into our line integral, we see that we have the integral of y dx plus the integral of y cubed dy. But for this integral, since we're on a straight line, a vertical line, we're not changing along the x-axis. So dx is equal to 0. So that makes this integral equal to 0. So then we just have this integral left. And that integral is equal to y to the power of 4 over 4 from 0 to 2. Or 2 to the power of 4 over 4. And that's going to equal 4. So now we have 2 out of the 3 completed. And the final one that we're going to do is the one that's along the line y equals 2x. So that's going to be this line here. And when y equals 2x, dy equals 2 dx. So we're going to use this to convert our dy integral into a dx integral. So for this integral, where it was x times y, we're going to substitute that with 2x. And for this integral, where it was y cubed, we're going to substitute it with 8x cubed. And dy will be substituted with 2 dx. And these integrals are from 1 to 0. So then we solve these integrals, and we get 2x cubed over 3 plus 16x to the power of 6 over 6 from 1 to 0. And we get minus 2 over 3 minus 8 over 3, or minus 10 over 3. And then finally, the last step is to add up all of these together. So we have 0 plus 4 minus 10 over 3. And when we add all of those together, we get 2 over 3. So we see that no matter which way we use, we get the same answer.